Here's a question that nobody was asking about 3I Atlas 6 months ago. What happens if you set it on fire? Not a regular fire, not a chemical reaction, something far more powerful than that. A nuclear chain reaction. The kind that powers hydrogen bombs. The kind that makes the sun shine. The kind that, if it ignited inside 3I Atlas, would release energy equivalent to 10 teratons of TNT. That is 200,000 times more powerful than the largest nuclear weapon ever detonated on Earth. And a Harvard astrophysicist just published a paper asking whether that scenario is physically possible. The answer he got back from the math is not the one most people expected. Subscribe to Space Aquarius and let's begin. To understand why this question even exists, you need to understand one of the strangest things scientists have found inside 3I Atlas. The deuterium. You already know deuterium is a heavier form of hydrogen. 1 proton, 1 neutron, instead of just 1 proton. Same basic chemistry as regular hydrogen, but heavier. And you already know the deuterium levels in 3I Atlas are extraordinary. The water around 3I Atlas showed a deuterium to hydrogen ratio of about 0.95%. That is more than 10 times higher than any known comet. The methane showed a deuterium to hydrogen ratio of about 3.31%. That is roughly 1,000 times above the average cosmic value found elsewhere in the universe. About 14 times higher than the methane-deuterium ratio in Comet 67P, the most studied comet in history. Those numbers are already strange enough on their own, but here's the part that Avi Loeb focused on in his April 2026 paper. Deuterium is nuclear fuel. Deuterium and its close relative tritium are the primary fuels used in hydrogen bombs. They are the fuels that power thermonuclear weapons. And they are the fuels that scientists around the world have been trying to harness for decades in fusion energy research. When 2 deuterium nuclei fuse together under the right conditions of temperature and pressure, they release an enormous amount of energy. That is the same basic process that powers the sun. And 3I Atlas is packed with it. So Loeb asks the question that follows naturally from that fact. If something triggered a nuclear explosion inside 3I Atlas, would the deuterium ignite? Would it chain react? Would 3I Atlas become, in effect, a gargantuan nuclear bomb? To understand why that question is not as far-fetched as it sounds, you need a little history. During the Manhattan Project in the 1940s, the scientists building the first atomic bomb were worried about something. Edward Teller, one of the most brilliant physicists of the 20th century, raised a speculative but terrifying possibility. What if the fireball from an atomic bomb explosion was hot enough to ignite the atmosphere? Specifically, he was concerned about nitrogen in the air. Nitrogen nuclei under extreme heat and pressure can potentially fuse. If the atomic bomb triggered a fusion chain reaction in the nitrogen surrounding it, the fire could theoretically spread through the entire atmosphere. The Earth's air would burn. That concern was serious enough that the Manhattan Project leadership commissioned a formal study. Hans Bethe, another legendary physicist, ran the calculations. He concluded that ignition of the atmosphere was extremely unlikely because of radiative losses. The energy would bleed away as radiation faster than the chain reaction could sustain itself. A formal report authored by Emil Konopinski, Cloyd Marvin Jr., and Edward Teller in 1946 concluded that whatever temperature a section of the atmosphere might reach, no self-propagating chain of nuclear reactions was likely to be started. The bomb was detonated. The atmosphere did not catch fire. But the concern did not disappear entirely. Throughout the entire nuclear weapons test program, similar questions kept coming up. Could a powerful underwater hydrogen bomb test ignite the oxygen in seawater? Could a large enough explosion trigger a chain reaction in some other material? Each time, theoretical and experimental data provided reassurance. But the underlying question, under what conditions can a nuclear explosion trigger a self-sustaining chain reaction in surrounding material, remained a live scientific question. And now in April 2026, Avi Loeb applied that same question to 3I Atlas. Here is the specific scenario he was analyzing. After the 1994 impact of Comet Shoemaker-Levy 9 on Jupiter, Teller himself proposed a planetary defense concept. He suggested designing a nuclear explosive device equivalent to about 1 gigaton of TNT, roughly the kinetic energy of a kilometer-wide asteroid, to protect Earth from similar impacts. The idea was straightforward. If a large object is heading toward Earth, You detonate a nuclear device at its center to break it apart before it hits. Loeb took that concept and applied it to 3I Atlas. If 3I Atlas were heading toward Earth and humanity decided to use Teller's envisioned device to destroy it, what would happen? Specifically, would the nuclear explosion ignite the deuterium-rich nucleus of 3I Atlas? And if it did, how much energy would be released? The math starts with the mass of 3I Atlas. Based on the non-gravitational acceleration data, Loeb and his colleagues estimated the minimum mass of 3I Atlas at approximately 160 million metric tons. That is an enormous amount of material. Now, if the deuterium content of that material matches the measured ratio of about 1 deuterium atom for every 30 hydrogen atoms in the methane, and you calculate how much energy would be released if all of that deuterium underwent fusion, you get a number that is almost hard to say out loud. 10 teratons of TNT. The largest nuclear explosion ever triggered on Earth was the Soviet Union's Tsar Bomba, detonated on October 30th, 1961. It released about 50 megatons of TNT. 10 teratons is 200,000 times more powerful than the Tsar Bomba. Teller's device in this scenario would be the match. 3I Atlas would be the fireball, and the fireball would have 10,000 times more energy than the match that lit it. Now here's the critical question. Would the chain reaction actually sustain itself? Or would radiative losses stop it? The same way Beth had calculated that radiative losses would stop the atmosphere from igniting in 1945. This is where Loeb's back-of-the-envelope calculation gets genuinely important. For a chain reaction to sustain itself, the energy released by the fusion has to raise the temperature of the surrounding fuel fast enough that the fuel ignites before it has a chance to cool down. The cooling happens through radiation. Hot material radiates energy away. If it radiates faster than the fusion releases energy, the chain reaction dies. For the atmosphere in 1945, Beth calculated that radiative losses would win. The atmosphere would not ignite. But 3I Atlas is not the atmosphere. The atmosphere is a gas. It is transparent. Radiation escapes easily. 3I Atlas is a solid, opaque object at solid density. In an opaque object, radiation does not escape freely. It gets trapped inside. It bounces around. It heats the surrounding material instead of escaping into space. Loeb's calculations indicate that for an opaque object like 3I Atlas, radiative losses occur primarily at the surface of the object, not throughout its interior. And his preliminary estimates suggest that the energy released by Teller's device would be sufficient to disintegrate 3I Atlas in about 1/100th of a second. In that time frame, the surface temperature would need to rise to a few million degrees to radiate away enough energy to compete with the fusion reaction. But a few million degrees is exactly the temperature at which deuterium ignites. In other words, the conditions required to stop the chain reaction through radiative cooling are the same conditions that would sustain the chain reaction through fusion ignition. The two processes are racing each other. And Loeb's preliminary estimate suggests that in an object as dense and opaque as 3I Atlas, the fusion wins. The energy released is sufficient to bring the fuel to ignition temperature before it has a chance to cool. A detonation wave would form. It would propagate outward through the nucleus. It would ignite fresh deuterium as it went, and it would continue until it reached the surface and destroyed the entire object in a single catastrophic explosion. Now let's be clear about what this means and what it does not mean. 3I Atlas is not heading toward Earth. Its current trajectory carries it away from the inner solar system, toward the Gemini constellation at over 130,000 miles per hour. Nobody is planning to detonate a nuclear device inside it. And Loeb is not claiming that 3I Atlas poses any immediate threat. What he is saying is something more subtle and more important. If humanity ever discovers an interstellar object similar to 3I Atlas heading toward Earth, and if the instinct is to use a nuclear planetary defense device to destroy it, the deuterium content of that object needs to be measured first. Because if the object is as deuterium-rich as 3I Atlas, detonating a nuclear device inside it would not solve the problem. It would create a problem 200,000 times larger. Loeb's conclusion is direct. We should be careful about using Teller's device for planetary defense against deuterium-rich interstellar objects. We need an alternative, and we need to figure out what that alternative is before we need it. The deuterium anomaly in 3I Atlas was already one of the most striking chemical discoveries in the history of interstellar object research. Levels 10 times higher than known comets in the water, levels 1,000 times above the cosmic average in the methane. But Loeb's April 2026 paper added a dimension to that anomaly that nobody had considered before. The deuterium is not just a chemical curiosity, it is a fuel reserve. And if the right trigger were applied, it could release energy on a scale that dwarfs every nuclear weapon ever built by a factor of 200,000. That is what makes 3I Atlas genuinely unlike anything we have ever encountered. Not just the trajectory, not just the jets, not just the chemistry. The fact that this object, if ignited, would be the most powerful nuclear event in the history of our solar system. And it passed through our neighborhood at 130,000 miles per hour, without anyone fully appreciating what was inside it. If this video got you thinking, subscribe to Space Aquarius so you do not miss what comes next. Leave a comment and tell me whether you think the deuterium levels in 3I Atlas are a natural anomaly or something that deserves a harder look. And share this with someone who has been following 3I Atlas from the beginning. This is the chapter they have not heard yet.